In this video, we are going to begin to talk about dimensioning. I cannot stress how important dimensioning is. The purpose of dimensioning is to provide clear and complete description of an object. A complete set of dimensions will permit only one interpretation needed to construct the part or the drawing or the whatever it is you're constructing. Again, it's extremely important. This is one of the biggest complaints we get from our advisory board and from people that our students go to work for, that you are not good at dimensioning. So please pay very close attention to this. If you are a drafting student, you will also have, if you haven't already, geometric dimensioning and tolerancing. Again, it's extremely important. So let's get on with learning about the 57 golden rules of dimensioning. So we're going to get started today. This first video is going to basically just go over the PowerPoint on dimensioning. And then I will follow up with another video that will actually go through the AutoCAD on how to do dimensioning. So the objectives that we want to cover are first to define the size and location dimensions. Those are the basic dimensions that we use. Explain the drawing conventions used for dimension, extension, and leader lines. Describe standard conventions used in inch dimensioning and metric dimensioning. Identify and explain common dimensioning systems used in drafting. Explain the purpose of general and local notes. List the general rules for good dimensioning practice. Describe the common commands and methods used in dimensioning CAD drawings and dimension drawings using accepted conventions. Dimensions. It's very, very important that they are legible. That would be the correct appearance and accuracy to make them work for our detailed drawings. Typically, if you were drawing by hand, all line elements should be drawn thin. Again, AutoCAD is going to cover a lot of that for you. Again, there are standard conventions used in dimensioning. The main one that we're going to talk about is ASME Y14.5. I will say at this point that dimensioning on mechanical drawings is a lot different than dimensioning on architectural drawings. And as we come across those points, I will make sure that you know the differences between the two. We have two types of dimensions that we do. One is the size of an element or a feature on our drawing, and the other is to locate. We have to be able to locate those. If you look at this, you'll see that this is a size dimension. It's from the end of the object to the other. These are location dimensions because they're locating the center of the holes in the object. And then again, we have to have a size for each one of these so they know how big to make the objects or the features in the object. You'll notice that we have an overall, then we have 3, and then we leave a dimension out. This is one of the differences between mechanical drafting and architectural drafting. Mechanical drafting, we always leave a dimension out. Architectural, we never leave a dimension out. But we'll talk about that more as we progress here. There are certain parts of a dimension. You have the dimension line, the extension lines, the leaders, the arrowheads, and the dimension figures themselves. The dimension lines are this portion of the line that you can see here. It is the line that is going from one dimension portion to the other dimension portion. There are certain spacing requirements. Again, when we drew by hand, we were very particular about this. Luckily, with AutoCAD, it makes this a little bit simpler. I'm not going to be as specific as maybe some of your other instructors might be. We have certain instructors that teach that are very, very picky about the dimension lines and such, but as long as you do proper spacing and the dimensions are legible, I am good with that. There are different ways to place a number. This one shows the number above the dimension line. This one shows the dimension line broken and with a number inserted. Again, our CAD program is set up with a basic setup that can be modified. When we get into AutoCAD, we'll talk about that. But for right now, keep in mind that it can be done differently depending on where you work at. The extension lines, these are the lines that come off of the object that the dimension line fits within. So those are important. And again, we try not to cross dimensions, but like in this case, this arrowhead does come across that extension line. So again, just trying to make them as neat as possible. That is important. You'll notice there is a little gap between the end of the object and where that extension line starts. AutoCAD is going to do this for you. You can adjust those. Everything in AutoCAD, as far as dimensioning, can be customized. The extension lines are used to indicate the termination of the dimension. Spacing conventions apply, and lines crossing with others should be broken. AutoCAD doesn't necessarily do that. We'll just go with the default settings in AutoCAD. Leaders. These are commonly used to show notes and repetitive features. They have an arrowhead used to terminate the edge, and sometimes if we're trying to show something different, we may use a different type of ending on our leader line. In this case, it's a dot, and it's indicating what the material is on this surface. Again, AutoCAD, we can adjust all of that. We can have the different ones. If you do these at an angle like this, they should be between 45 and 60 degrees. We want everything to be as neat as possible. Dimensional notes. Here is how we can do a chamfer note. There are other ways to do chamfers with dimensioning. This is good for mechanical drafting. In architectural drafting, contractors don't like to work with numbers like this, so we would actually dimension the offsets for each of these, but we'll talk about that more in a minute. Holes. Holes are usually always going to be shown as a diameter, okay, not as a radius. We use radius for our fillets and rounds. In this case, this note is saying that there are 6 holes that have a diameter of 0.089. So if they are all the same, we don't have to put a note on every single one. That makes our drawings way too busy. And then of course we have thread notes. Arrowheads. Again, this all has to do if you were drawing these by freehand. These are generated automatically in CAD. You can adjust them in CAD, and we will talk about that when we get to AutoCAD dimensioning. Dimension figures. These numbers that go with our dimensions should be at the same height as our lettering height. Again, that is 0.125 is what we typically want. Fractions are typically drawn at twice the height of the whole numbers. Again, AutoCAD is going to do that automatically. Sometimes we like to stagger numbers so that it makes it easier to read. So here is an example of fractional dimensioning that we use in architectural drafting. Again, in architectural, sometimes the 1 is a 1/2, but again, AutoCAD will set that up for you. In mechanical drafting, the 1 and the 2 are on top of each other. That is a common practice in mechanical drafting. Here is an example of a decimal inch or metric dimensioning, the 1.5. Dual dimensioning. Sometimes we have to do dual dimensioning. I had a project that I worked on at Architectural Components Group that was a project in Canada. In Canada, they use the metric system. So when I did my drawings for them to review, I had to include the metric dimension for the architect in Canada, but I had to use the inch dimensioning for our factory to be able to make the products. So again, AutoCAD will do this for you. You can select to do either type of dual dimensioning. Staggering dimensions. Again, with AutoCAD, it kind of does things automatically. It always centers the numbers within there, but you can adjust them. But a lot of times we don't like the numbers to be up and down in line with each other, because sometimes it's very easy to mess up the numbers by doing that. So again, AutoCAD's going to kind of automatically do this for you because it's going to center the numbers in the dimension line. Dimension placement systems. We don't typically do aligned dimensions. We always like our dimensions to read in this horizontal manner. So again, with AutoCAD, you can set it up either way. This is likely going to be the standard in most places that you work, but there is a potential that other companies could do it like this. So you need to know how to be able to set that in the AutoCAD dimensioning tools. Dimensioning within an object and outlines, used in some cases for calling out feature directly. Section lines broken when used on section views. When we get ready to look at your assignment for this dimensioning section, you're going to see 57 golden rules of dimensioning. Again, I'm not as picky as potentially a mechanical drafting instructor might be. Most of the time, we try not to dimension dimension on the object. We always try to dimension outside of the object. Sometimes, to me, that's not practical. As long as you dimension on the object and I can read it, I do not have a problem with that. But some of your other instructors may. So it's probably best just to try not to do it. This one here, we definitely don't like to do on section views because it makes it very hard to read. If I put my dimension in first and then I put in my section marks, it will break the section marks in AutoCAD so that the number does show a little bit more legibly. But again, in this case, I would pull this dimension out to the side instead of putting it on the object. Dimensioning systems. We can have decimal inch dimensioning, fractional dimensioning, metric dimensioning, and dual dimensioning. Decimal inch dimensioning is commonly used in manufacturing applications. So again, more on your mechanical and technical types of drafting. Two-place decimals is most common. But as you know, with AutoCAD, we can go much further in our placing of the decimals. Depends on how accurate the part has to be. Common rules apply when rounding off values. If it's above a 5, it's going to round it up. So that's where we can run into problems if we're not accurate in our drawings. So here's some example. A common decimal value used for a hole. Again, you'll notice it has the diameter symbol. There are tools in AutoCAD to be able to do that. Nominal size fraction used for a thread note. When we have a diameter and number, we don't put the 0 in front of the 0.75. That makes it very difficult to read. And again, AutoCAD does this automatically for you. Decimal point, it should be aligned with the text, and again, AutoCAD is going to do that for you. Fractional dimensioning. This is what we commonly use in architectural and structural drafting. Used for applications where close tolerances are unimportant. And a horizontal bar used for fractions, but you can also use the diagonal bar. In architectural and structural drafting, tolerances are not typically as important as they are in mechanical drafting. Architectural and structural construction are not exact sciences. We don't have machines out there to set things perfectly as we do in a manufacturing atmosphere. We like to use a lot of plus minus so that we can make adjustments as things need to fit. Metric dimensioning. Millimeter dimension drawings are the most common. Meters are used for values that are greater than 10,000 millimeters, and this is based on the International System of Units, or the metric system. We don't typically use this in the United States, but if you work with companies that are outside of the United States, a lot of the rest of the world does use the International System of Units, or the metric system. Metric dimensioning conventions. Period is used for the decimal point. That's an ASME standard. 0 precedes decimal for values less than 1 millimeter. Digits are not grouped by commas or spaces. Typically, like if we say 1,000, we do 1, comma, 1, 2, 3 zeros. In the metric system, they do not do that. They would just do 1, 0, 0, 0. Multiples of 1,000 are used for units, use of centimeters avoided, and units not mixed with other systems. I realize this video is a little bit long and boring, so we're going to take a break and we're going to have a brain break.
Stand up, feel the beat, and let's do the happy dance. I'm so happy, that's why I clap my hands, because I'm feeling happy. I'm so happy, that's why I twist my hips, because I'm feeling happy. I'm so happy, that's why I march in place, because I'm feeling happy. I'm so happy, that's why I wave my arms, because I'm feeling happy. Happy is a feeling I like to feel, and I like to spread it too. I'm happy just to be here singing the song and dancing along with you. Dance your happy up, dance your happy down, dance your happy side to side and dance it all around. Dance your happy up, dance your happy down, dance your happy side to side and dance it all around.
I do realize that's about a minute of your life you will not get back, but hopefully it at least made you smile for a minute and brighten up your day a little bit. So now we will get back to dimensioning. Dual dimensioning. Inch measurement typically given in decimal inches. Metric measurement typically given in millimeters. Metric only drawings are more common. Depending on what kind of a product you're doing, what kind of a project you're working on, you may have to use the dual dimensioning. There are a couple of different ways it can be done, and again, AutoCAD will allow you to set this up however you want. Typically, this is the most common that we use in the United States. We put the inches or the architectural units like we use above the line and the metric dimension below. On the right, you see we have the metric dimension above and the inch dimension below. And again, that's going to be used where they use the metric system more. And then there is another way that you can do it so that the millimeters are in a bracket and the inches are not. That is the style that I used when I did my drawings for the project in Canada. Features dimensioned for size. There are lots of different types of features, as you can see on here, that need to be dimensioned so that they know how to make that feature. We have cylindrical features, circular arcs, fillets and rounds, round holes, knurls, angular dimensions, chamfers, counterbore holes, spot-faced holes, countersunk holes, counter-drilled holes, offsets, key sets, undercuts, tapers, curves, and slotted holes. And there could be even other specialty features depending on the part or the object that you're making. So for cylindrical features, we have some certain conventions that we use as far as dimensioning. Used for solid shapes and negative volumes, which are holes. Diameter and length specified. Diameter symbol used. If you look over here to the right, single view with diameter dimension. If I did not put that diameter symbol there, I would not know that this is a round object. So if I just put 1.5 and 11 here, I would just think this was in a rectangular piece. Over here, we have two views with leader dimensioning. So you have over here, again, because of the side view here, I have to put the diameter symbol here to know that this is round. Notice that the hole is dimensioned in this view and not in this view. We'll talk about this more in a little bit. We do not dimension to hidden lines unless we have no other choice. This is another way that we can do it. In this case, you don't have to put the diameter symbol because we can see that it is round. Circular arcs. Typically, when we have a fillet or a round, we go by the radius and not the diameter. So the radius is specified, value is preceded by R. Again, AutoCAD will do this automatically for you. Dimension line typically drawn from the center of where that fillet or round is, and leader dimensions may be used. So in this particular case, again, we have a round and we have a fillet. So from the center mark of that, it will show that. Sometimes it's too small to put in within there, so AutoCAD will automatically pop it outside for you. This one is a leader dimension. This one is not done with a dimensioning tool. This is done with a note tool. Again, it's best to use the dimensioning tool to do that. Center location indicated by the crosshairs. Again, on this particular object, we need to know where that center point is. Sometimes our object is way too big to be able to show where the true center point is at. So we can do foreshortened dimensions. Again, this isn't real common because with AutoCAD, we have a lot more flexibility on how we do things. Dimensioning true radii. This is done to clarify measurement appearing out of scale. Note includes specification. As you see here, we have the true radius here, and then we have one that is not. So this is the recommended to say true so that we know that that is the true radius. This one could be misleading and could cause errors. Conventions for fillets and rounds. Typically, again, as I said, the radius is what's specified, and a note is used for many features of the same size. So again, over here we have the radius of all of this. Now notice we don't have to dimension over here because we know it is symmetrical and can do that. Another way we can do it, if all of the radius or radii are the same, we can do it with just one note. For round holes, again, a hole, we're always going to use the diameter. The leader dimensions are used for smaller holes, dimension lines used for larger holes, and the hole depth indicated by a note or a section view. So here, this is telling me that we have a diameter that has a tolerance, meaning that hole can be between 0.38 and 0.375, and it is a countersunk hole that goes down 0.75. So basically, from here to here is 0.75, and the diameter is this. Again, like we talked about a while ago, this is another way for doing the holes, and in this case we don't have to do the diameter symbol because we can see that it's round. This one here, we have the diameter that also has a tolerance, another way with a tolerance, and another way with a tolerance. And again, we can do just a section view also that will tell us exactly how this works. So there are several different ways to do this. Your company will have a standard on how they want things done. Knurls. If you don't know what a knurl is sometimes you've seen like maybe on a socket or something where it has part of the handle that kind of has a rough surface on. That is done to help grip, to be able to grab and to turn. If it's completely smooth, sometimes it's hard to get enough grip on that. So a knurl is a pattern on a piece of metal. And it can have different patterns, like it can have a straight pattern, it can have a diamond pattern, etc. So the important things on knurls is to put in the diameter, the type, and the pitch specified by a note. The length along the axis specified if required, and the size and location dimensions typically combined. So here we have a raised diamond knurl, and it tells where it starts, what the diameter is, and how far the knurl comes out. So again, putting all of that information on there is very important for manufacturing of that part. Angular dimensions. Again, there are several different ways to do it. Depending on your company, they are going to have specific ways they want things done. AutoCAD will do a degree just like this. This one is more of a surveying type, 0 degrees 15 minutes. This has to do with surveying information. You can do degrees in decimals. Typically, even in architectural, when we put in an angle that has a partial, we usually do that in decimal degrees. This is what's most common used in architectural, because if I tell a contractor I need something to be at 38.7 degrees, he's probably, unless he has a laser, not going to know how to do that. So I typically would give him the 2 dimensions to be able to lay out the points to be able to get that angle correct. Chamfers. Again, there are different ways to do chamfers. Here is a very common one, that it is 0.12 times 45 degrees. That means it is 0.12 long at 45 degrees. These are external chamfers. Again, it can be done by a dimension and an angle. That's also common. And here is another one for internal chamfers. Conventions for counterbore and spot face dimensions. A counterbore or a spot face, they have symbols. And again, AutoCAD has all of these symbols for you. Now, if I use my AutoCAD dimensioning tool, it will give me the diameter of 8, but it will not give me this part of the dimension. So I have to go in and manually add that in, and I will show you how to do that. So there again, you need to specify the diameter, and you want to use the symbol appropriately. Countersink and counter drill. Again, I can use my AutoCAD dimensioning to do this portion, but I will have to go in and add the rest of this. This is just a basic dimension. Again, how to do these over here. Offsets. You typically will dimension from tangent points of intersections and dimension along one side of the part. So I have basically located horizontally where these 2 curves take place, and I've dimensioned from this point to this point. So again, whatever information you need to give so that they can build the part. Key sets. If you're not sure what a key set is, this is the part that has the key set actually in it. And then what they would do is they would have another part that goes around it that would lock into this little inset here. So again, dimensioning those appropriately is important. So again, these are examples of a regular key set and a Woodruff key set. Undercut dimensions, this is kind of messy, okay? We run into this a lot because some parts are very, very small and it makes it very, very hard to read. So sometimes just doing it with a note might actually be better. These are all the same. So I could have used just one note to do that. If it has a little round in it, then I would want to do and call out the radius for that, just like I normally would. Tapers. Tapers are kind of interesting on how we need to do them. This is a taper symbol. And again, with my courses, I don't really get into all the different types of symbols as much as in your mechanical classes. So again, we have an overall diameter here. We have to the center point, and we have some points so that we can work off of that. So this is a basic taper and basic diameter given conical taper. Tolerance diameters and tolerance length given conical taper. Again, AutoCAD will allow you to set the different types of tolerances and will put that into your dimensions for you. Tolerance slope and tolerance height given on a flat taper. So again, you can refer back to this PowerPoint if you ever need to look into any more of the dimensioning. Curves. Curves are always fun to try to dimension, especially when they're not a regular curve. Architects like to use weird shapes. Sometimes parts need to be odd shapes. So here are some examples of how you can do that. This one is working off of datums, and we'll talk about that more here in a minute, where we work off of this corner point and we establish points along the way, and we can connect those points to create that curve. This one is one that is symmetrical about the center line, so we can dimension the different points and do the distances in this direction. So again, depending on what you're trying to accomplish, your company will have standards on how they want things done. Rounded ends. This is a fully rounded end, radius indicated but not dimensioned. So we have the radius here, we have the overall, so we should be able to figure out what the distance from here to here is because we know what this radius is. Partially rounded, again, this radius is not the same as the height of this, so again, we have to specify so that they know how to build it. Slotted holes. This is where things can get a little bit messy. You need to specify the length and the width and the longitudinal center or one end or center line located. So here are some examples of how those can be done. Now we get into the methods for dimensioning features for location. We have point-to-point dimensioning, we have coordinate dimensioning, tabular dimensioning, and ordinate dimensioning. Point-to-point dimensioning is probably the most common. It can also be called chain dimensioning. This is acceptable for simple parts. And again, in mechanical drafting, one dimension is omitted in the chain for manufacturing. In architectural dimensioning, we do not omit any dimensions. Mechanical drafters tease architectural drafters that they over dimension. Of course, I come from an architectural background, so I kind of lean on the side of over dimensioning. If we come in here and we have this part that has 3 holes in it, you'll see that we've located to the first hole, from that first hole to the second hole, from the second hole to the third hole, and the overall. This dimension is left out because if there's any variation in the part, this is where you want that variation. This is very important that these be lined as they are. And of course, this way we have the overall, and then we just have one dimension and we've left out the other dimension. Coordinate dimensioning, both types incorporate datum dimensioning. You have rectangular coordinate dimensioning and polar coordinate dimensioning. Rectangular and polar coordinate dimensioning. If we look at this, you can see we are working off of a datum plane here. So all of the dimensions to these first holes come up to here. We come off of our plane again and go to here. Our plane and here, plane and overall. Again, same way this way, from the plane, etc. Polar coordinate dimensioning. Again, we have 2 datum planes that we're working off of. We have the radiuses to each of the holes. Tabular dimensioning. If we tried to put dimensions on this part with all of these different holes, this would just be impossible to read. So what we can do is we can set up a form of rectangular coordinate dimensioning, and it's useful whenever you have many similar parts. So we have our overall dimensions, and then we have a code, letter code, on each one of these holes. So if I want to know about the hole A1, if I come down here to A1, it's going to tell me the X dimension, which is from here to here, is going to be 0.25. The Y dimension, which is going to be from here to here, is 0.625. And then it's going to tell me the diameter of that hole. So again, sometimes doing a tabular dimensioning is much simpler than trying to put all of those dimensions onto the part. Ordinate dimensioning. This one is not used real commonly, but it is a potential that you might run across. So datum planes specify 0 coordinates. So we start at this corner with 0 and 0. The extension lines indicate the dimensions. So from here to here is 0.25. From here to here is 0.93. From here to here is 1.83. From here to here, so it's giving me specific numbers to each of these locations. Again, this one doesn't have any arrows on it, okay, because it is an ordinate dimensioning style. Unnecessary dimensions. As I mentioned, 1, we always leave out a dimension. Second rule, and out of those 57 rules, these are the ones that I do look for. Do not duplicate dimensions. If you duplicate dimensions, that leaves us the potential to have errors in our projects. Accumulation of tolerances is avoided in chain dimensions, and exceptions occur in architectural and structural drafting. As I mentioned, we dimension everything and we over-dimension in architectural and structural drafting. So this dimension here is being eliminated because I don't want all of the dimensions across here. I have this one, this one, this one. I don't need that one. I have my overall. I do not need this one because that comes from this, so I do not need that. Again, we don't typically dimension hidden lines. I need to eliminate those. And again, I have 0.75 here, so I don't need 0.75 here. So again, do not duplicate dimensions, but make sure you have everything dimensioned correctly. Notes. Sometimes just having dimensions is not enough for our projects. We need to have some notes to clarify information and eliminate repetitive dimensions. They are typically aligned parallel to the bottom of the drawing. They should be the same height as all of our other lettering and dimensions. Again, the spacing, we don't need to worry about that too much. And make sure if you're using abbreviations, you use standard abbreviations. Don't make up your own abbreviations. There are standard abbreviations used for different things. We have 2 types of notes. We have general notes, and these are used for information applying to the entire drawing. They are typically placed near or inside your title block, and they are often used to identify tolerances or materials. So if we use the same tolerance on making this whole part, we can just put that as a note in our title block, and that will keep us from having to repeat that on every single dimension. Then we have what we call local notes. They may also be called keynotes. These are used to describe specific information. They are typically connected to leaders originating from whatever you're trying to call out, and may be used with reference number and flag. That's where we would call them more like keynotes instead of local notes. Sometimes it's easier to have a legend that has several notes in it, that has a number associated to it, and you just point with a number to whatever you're trying to reference on your drawing, and then you can look in the legend and find what that is. Keeps our drawings a little bit neater, especially on the architectural side, because we have so many notes. So here are some examples. Right down here at the bottom, you'll see there is a general note. It says remove all burrs and sharp edges. So instead of placing that note on each side of this part, we can say that as a general note. Here is a local note. Machine these surfaces flat and square after welding. So those two surfaces need to have some particular finish to them, so that's why we would use a local note. Another general note, as we talked about, is the tolerance. So the tolerance is acceptable for everything on here unless it's noted otherwise. Again, instead of placing that on every single dimension, we place that in the title block. Rules for good dimensioning. Now, some of these rules are the ones, again, that I go by. I do want you to look at the 57 golden rules, I believe they're called, because some of your instructors may require a little bit more than what I require, or your employer may. Plan layout to avoid crowding. This is a great advantage to AutoCAD. We can always move, stretch, pull things, whatever we need to do. But again, when we typically are drawing our multi-views, things like that, we may have them kind of crunched together, so we may need to spread them out once we start adding dimensionings. Draw all thin lines. Again, AutoCAD's going to do that for us. Dimension the most descriptive contours. That's very important. Place dimensions between views and outside of the outlines. Again, we don't want to put dimensions on the object if we can help it. Avoid crossing lines. This is one of my #1 pet peeves. Talk about that when we actually get into AutoCAD and showing you how to do that. Dimension features to show relationships. Dimension visible features. All features need to be dimensioned and located. State the information clearly. Include enough information to eliminate calculations. Include only essential information. And again, omit one dimension in chains. First, I want to say congratulations. You made it through the Dimensioning 57 Rules lecture. If we go to our home page and we scroll down, you'll see the dimensioning page with 57 golden rules. At the top, you also have a reading assignment that goes with the AutoCAD portion. The video will be placed here once I get it completed. Don't forget your previous assignments. Also, make sure you read the do's and don'ts of dimensioning. This is a PDF, and you need to be sure to read through that, especially if you're going into mechanical engineering or drafting. These rules are extremely important. The rest of the page gives a synopsis of what we've talked about today, and at the very bottom, you're going to see that you have some review questions. Next, we will move into AutoCAD and learn how we apply these 57 golden rules to AutoCAD and to our drawings.